Thanks. So today I'll talk about some preliminary results that we've got using MVAPICH2-X on STSC Gordon cluster. I want to acknowledge a couple of the NSF grants that are supporting the work. So start off with some info on Gordon itself. It was essentially designed as a data-intensive computer, focusing on different kinds of I/O. So it was one of the first machines to have a large-scale flash deployment, 300 terabytes of Intel flash in it. We also had the ScaleMP software to enable VSMP, virtualized shared memory machines. It features a dual 3D torus interconnect from Mellanox. I think it was one of the first machines to do that also. It's been in production since February of 2012, funded by NSF, and it's available through the Exceed program for users. So I'll start off with a sub-rack level diagram to just show the connectivity on the machine. So on Gordon, essentially, there are two rails, so rail 0 and rail 1. And it's a torus of actually switches. So it's a 4x4x4 torus of switches. And each switch essentially has 16 compute nodes and an I/O node attached to it. And the SSD flash actually resides in the I/O node and is exported using iSCSI to the compute nodes. And it can be used in any way that's needed on the compute node. By default, what we have is a file system on each compute node with 300 gigabytes of flash. And you get about 250 megabytes per second on each of the flash drives there. The other thing the I/O node serves as is the router for all the raster traffic. So what we have is preferential routing through the local I/O nodes. So if you're doing intensive I/O out of those 16 nodes, you're going to mostly go out of the local I/O node, so you're not overloading the 3D torus network with the I/O traffic. And actually, the I/O nodes are connected to the Lustre file system using two 10 gig links. So we have a total of 64 of these I/O nodes, so you end up with 128 10 gig connections out. We've sustained 100 gigabytes per second to the Lustre file systems. So the network itself is a 3D torus of switches, and as I mentioned, it's two 3D torus networks. This is just one of them. So each of those yellow boxes is the sub-rack that I showed in the diagram. And it's a 4x4x4 torus. I don't have the loop back on the Z direction just to not complicate the story. So it's linearly expandable. I think the max hop count is 6. Much lower cost, of course, and easier to handle. Since we have dual rail, we have a bit of fault tolerance from there and from the torus network itself. And those are the gory details. I think the only thing I want to mention is we have 64 gig of RAM per node, so it works out to 4 gigs per core, and 300 gigabytes of SSD, as I mentioned. And it's dual QDR on the InfiniBand network. So I'll start off with OSU Microbenchmark results with the MVAPICH2 environment. So the software environment itself for today's results, what I used was MVAPICH2-X version 2. I think this is the June 20th release with the Intel compilers. So it's unified support for MPI, UPC, OpenSHMEM, and OpenMP. Also have the Berkeley UPC 2.18.2 and the GasNet version 1.2.4 using the IBV conduit. And for OpenSHMEM, I use the release version from I think University of Houston. So before I jump into the OpenSHMEM and UPC results, I just wanted to go over the MVAPICH2 dual rail performance, and this is from our Exceed 14 paper. So we looked at actually both microbenchmarks and application performance. For today, I'm going to show you the performance just from the microbenchmarks. So latency, bandwidth, look at comparisons between single, dual rail, QDR, and FDR. And FDR, I think the tests were done on Stampede. So we're going to evaluate the impact of rail sharing, scheduling, and threshold parameters, and it's pretty standard stuff for dual rail MVAPICH. So the first plot I have is essentially test results with single rail QDR, FDR, and dual rail QDR, and this is a bandwidth test just with 2 nodes and 2 processes essentially. And what we did is just out of the box default settings for all the thresholds and the round robining. So the single rail, I mean, of course, FDR is much better than the single rail QDR as expected. At the dual rail QDR actually does a little bit better than the FDR performance at the larger message sizes. But of course, you can see out here near the 16K region, FDR is doing much better. So, and that jump essentially is the threshold for the dual rail sharing. So that's the 16K default threshold that happens. So one easy way to fix that is actually drop the rail sharing message threshold to 8K, and you get a much better performance even at the smaller message sizes, and it bridges some of the gap. The other thing you can do is actually explicitly do the rail sharing round robin for all message sizes. And that's this dotted black line out here. And you can essentially match the FDR performance at the lower message sizes and, of course, exceed it at the upper end. So we did pretty well with dual rail QDR application performance also, as you might expect. Now, one question might be, what does this do to the latency? So the latency results show that actually the dual rail with the both rails being active for all message sizes is a little worse than the QDR latency, but it's still better than the FDR latency on the smaller message sizes. So those are results where we're using MVAPICH2-X with just pure MPI mode. So the next set of slides is essentially atomics and OSU benchmarks essentially for UPC and OpenSHMEM. So the first test case I have is the UPC memput benchmark MVAPICH2-X compared to the Berkeley UPC implementation. So in this case, you see that the latency, message latency, is pretty much identical for all message size, the whole range. And this is just with 2 tasks, 1 task on each node. So all we're doing is going over the IB for that piece. And memget does pretty well too. This is, I think, about 1.8 microseconds here, and the previous slide that was 1.5 microseconds at the lower. Right. So again, for the whole message size range from 1 to 4 meg, the latencies are almost identical. It's a slightly different story with OpenSHMEM. And I'm trying to figure out if this is okay or we have to do some more tuning on the OpenSHMEM side to get better results. And maybe someone in the audience knows better about this. So if you look at comparisons, again, it's MVAPICH2-X, and then I have OpenSHMEM version 1.0F. This is the release download from Houston, going over GasNet IBV. Again, just 2 tasks, 1 task per node, 2 nodes. And so the MVAPICH2-X implementation is pretty good. This is, I think, 1.5 microseconds again. Very similar to what we got for the UPC case. But the OpenSHMEM implementation is way off compared to that. I think that's a couple of things there. One is it's pretty variable, like the results are not repeatable in the same way. And it's, I think, 3 or 4 microseconds off compared to the MVAPICH2-X results. And the same, so you get the same kind of results with atomic benchmarks. Again, if you look at MVAPICH2-X, you get pretty good latencies and pretty stable across the board for all the benchmarks. So this is a bunch of additions and swaps and all kinds of benchmarks that you can go through. And it's very stable and pretty good numbers, I think, all across the boards. But when you look at the OpenSHMEM release implementation, it's higher again, like in the 5 microsecond latency range. And it's again very intermittent in terms of the performance. You get different, a lot of variation between runs. I have some really outlier results in red there. And the story really gets even worse when you start looking at collectives. So again, I just have 2 tasks and I start building up the number of cores per node up from essentially 2 tasks to 32 tasks. And again, MVAPICH2-X is doing pretty well with the barrier all across the board. And on the release OpenSHMEM, you can see it's not scaling very well going across. It's still 2 nodes, so you're not going across multiple nodes, and you would expect that to, remain almost constant there, but it's doing far worse. But again, I think I just use the default release with the GasNet IBV, maybe with some work that can change. So going to more collectives, so OpenSHMEM broadcast with 2 nodes, 8 tasks per node, so a total of 16 tasks. Again, message size so on the x-axis and latency on the y-axis. You can see MVAPICH is doing pretty well. That's, it's about 1.5 microseconds. And OpenSHMEM, the release version is off by, I think, almost 2 orders. So we're doing pretty good with MVAPICH. And on Gordon, I scaled it up to 512 cores. So it's actually 2 switches. I reserved 2 switches and kind of kept it together and did the broadcast test with MVAPICH2-X alone. And you can see we're doing pretty well going out to 512 cores. The range out here, I think, is between 1.5 and 6 microseconds, going out to 512 cores. So those were micro benchmarks and like very small test cases. And then on the application side, I started off with NAS parallel benchmarks. There were UPC and OpenSHMEM implementations available. I have the links there in case someone wants to download and test them. The UPC version is out of George Washington University, HPCL lab there, and the OpenSHMEM version is, I think, the University of Houston and Oak Ridge implementation. We also have some tests going with CP2K and PSDNS for like hybrid codes and some more work that's ongoing. I don't have results for that today. So with the NAS parallel benchmarks, I kind of looked at different components of it. So the first one is a CG, Conjugate Gradient, and I just grabbed the description from the NAS parallel benchmarks page. So irregular memory access and communication. Going again from 32 nodes to 256, it's all with MVAPICH2-X, and you can see they're scaling pretty well with the UPC version, going from 2 nodes out to 16 nodes on Gordon. So that's all on one switch right now. So what I have here is the node count, the core count, 32, 64, 128, 256, and the node count on the brackets. There's an integer sort benchmark, which is essentially a random memory access Again, it's MVAPICH2-X is doing pretty well, going out to 256 cores. And one thing I want to add is running this was really easy using MPI run RSH. Nothing special, just out of the box, install and run, and didn't have any issues. So again, nice parallel benchmark class D. This is a multi-grid case, so you have a sequence of meshes, and communication is both long and short distance. This is pretty memory intensive. I think on this benchmark I was using probably more than half of the memory on each of the nodes. And again, if you look at the results, we are doing pretty well in terms of scaling, even going out to 512 cores, which is actually on a remote switch on Gordon. Because when you get to 32 nodes on Gordon, if you don't specify anything, we actually distribute you over the whole machine, whatever is free. In my case, just for benchmarking purposes, I picked 2 switches close to each other. One thing I didn't mention in the earlier description of Gordon itself is that the switch-to-switch links are oversubscribed. So you have 3 switch links in each direction. So if you pick 2 switches next to each other and you're doing a lot of communication over it, you'll have a 16:3 oversubscription going directly there. So that was the UPC version. So I rated the same benchmarks with OpenSHMEM version. Again, MVAPICH2-X only. One different benchmark, the Scalable Penta-diagonal solver. So starting with 16 cores, and I think this benchmark needs the core count to be a perfect square. So that's why you have 16, 64, and 256. And you can see they're scaling really well, going from 16 cores to 256 cores. And this is using OpenSHMEM. Then we have the nice parallel benchmark, the class D multi-grid again, going from 16 cores to 256 cores. Again, even with the OpenSHMEM implementation, you get similar results to what we got. I think it's a little bit slower on the 64 and the 128 core. And it's again memory intensive, using quite a bit of the memory on each node. So overall, I think first look, it looks like it's really easy to use. I mean, I had no issues with compiling, running these codes. MPI run RSH just worked out of the box. A few parameters to set in terms of the heap sizes and things like that. But if you just follow the user guide online, it's pretty simple to implement. So we're going to continue investigating the performance results. This was early results where I just ran them and just looked at the numbers. I haven't really dug deep into communication patterns and things like that. So that's something I can look, especially the OpenSHMEM version. And we can test this at much larger scales. So Gordon, Stampede, and Comet's the machine that's coming up at SDSC. And we're going to have work that's ongoing with the PGAS project, which is going to look into hybrid code performance. Couple of things. I mean, one, PSDNS, Dimitri, who's at SDSC, is looking into the OpenSHMEM implementation. And lastly, I want to add to everyone's thoughts. I think a big thanks to Dr. Panda's team, I think, for all their work with MVAPICH2 and MVAPICH2-X. It's done great on all our machines, and we've got great support, instant responses on everything. So I think it helps a really big community. I mean, if you look at the NSF user base between, I think, Stampede and Gordon and all the machines, it's well over 10,000 users, I think. So